106 million cubic feet of solid rock must be extracted to prove that geography no longer dictates the rules of maritime navigation. Before an ocean that crushes massive ships like fragile toys, engineers have made a decision that defies standard logic by deciding to split an entire mountain in half to hide the sea within its core. Why spend nearly €1 billion to carve a hole through stone when the ocean exists everywhere around it? This massive investment is the price of overcoming a geographical trap that has claimed vessels for centuries. The answer lies in the unique and lethal nature of the Norwegian coastline, where a standard detour is no longer a viable option for modern logistics. The process is only gaining momentum. Engineers must drill through granite with millimeter precision to create the first ship tunnel in the world. It is visible how the heavy machinery penetrates the ancient stone, preparing the way for a passage that will bypass the most dangerous waters on the planet. At first glance, the Stad Peninsula appears inoffensive on a map, looking like a simple curve along the rugged coast of Norway. But in reality, for any sailor who has navigated the North Sea, this specific name triggers an immediate sense of dread. Everything only gets more complicated. The sea does not behave in a rational manner in this specific corridor. One can notice how the water changes its temperament as if an invisible hand were flipping a switch of pure chaos. In this zone, weather forecasts frequently prove useless, and survival often becomes a matter of sheer luck rather than technical skill. €1 billion is the calculated cost of bypassing this atmospheric instability. But this is just the beginning of the engineering challenges. What makes the Stad Peninsula so lethal? The equipment gradually moves into position to dismantle the mountain, as the project requires the removal of millions of units of debris. It looks superficially simple to sail around a peninsula, but the intersection of currents and underwater topography creates a maritime graveyard. Transition to the next level. The granite walls will eventually form a sanctuary for ships, shielding them from the crushing force of the North Sea waves that regularly exceed manageable heights. The rock faces split with a heavy crack under the pressure of industrial drills. This ambitious undertaking represents a permanent solution to a problem that has existed since the first ships began to trade along these northern routes. The material is ready to move to the next processing phase without haste. Thus, the transformation of the landscape begins to serve the safety of international shipping. 100 days per year is the minimum duration that this specific stretch of ocean remains a chaotic combat zone for any vessel attempting passage. Why do two separate bodies of water, the North Sea and the Norwegian Sea, create such a lethal environment at this precise geographic coordinate? The answer lies in the shallow underwater topography that forces these massive water masses to collide head-on, generating the phenomenon of crosswaves. These waves reach heights of 30 meters, matching the vertical scale of a 10-story building, and they do not approach from a single direction. One can notice how the water impacts the hull from multiple sides simultaneously, effectively turning the sea into a giant industrial washing machine capable of snapping reinforced steel casings in half. At first glance, it seems that a calm surface would follow the end of a storm, but in reality, the kinetic energy remains trapped in the swells for days after the winds vanish. Statistics from the era following the Second World War reveal a grim reality of 45 major accidents and the loss of more than 30 lives in these waters. It gets more complex further on. Norway operates as a global maritime superpower, moving 3 million tons of fish annually to 150 different nations across the planet. This dangerous passage serves as a vital commercial artery that cannot be abandoned despite the extreme risks to logistics and human life. Barges, passenger ferries, and heavy cargo ships are forced to wait for weather windows that might stay open for 4 hours or collapse entirely in just 30 minutes. It is visible how vessels hover near the edge of the peninsula, playing a high-stakes game of chance where the cost of failure is the total loss of the crew. Because the entire economy of the western coastline is held hostage by this geographical bottleneck, a radical engineering shift became necessary. The process is only gaining momentum. If the surface conditions cannot be conquered by traditional naval architecture, the transit must move beneath the Earth itself. The Stad Ship Tunnel is the proposed solution, appearing as a straightforward linear path on navigational charts between two distinct fjords. But this is just the beginning. In practice, this project represents the most massive terrestrial surgical operation ever attempted in the history of Scandinavia. This is not a standard bore for vehicular traffic, but a massive industrial corridor designed to accommodate the displacement of heavy seafaring vessels. The equipment gradually prepares to excavate a void through solid rock that will change the maritime map forever. 26 meters is the precise width established for the passage to ensure that robust cruise ships, equipped with high-reaching antenna arrays, navigate through the structure with total comfort and safety. Why is such a vast horizontal clearance necessary for a vessel inside a mountain? One might assume a narrower corridor would suffice for a hull, but the extra space prevents aerodynamic pressure and allows for stabilization during the transit. This width ensures that even the largest permitted vessels maintain a safe distance from the rock walls at all times. 3 million cubic meters of solid rock must be extracted by engineers to complete this monumental void. The sheer scale of this volume is difficult to comprehend without a physical comparison. It would require exactly 750,000 individual trips by heavy-duty dump trucks to move this entire mass of stone. This is not merely a construction project, but the systematic dismantling of a mountain, piece by individual piece. It only looks obvious to use massive detonations to clear the path, but in reality, the local geology demands a much more disciplined approach. One can notice how the equipment remains confined to specific zones rather than attacking the entire face. A single massive explosion is strictly forbidden due to the risk of structural collapse. Instead, the process is only gaining momentum through a specialized method known as layered construction. Engineers do not utilize a horizontal boring machine to drill through from one side to the other. It seems simple to follow a straight path, but the stability of the mountain requires them to excavate from the top down. First, the ceiling of the tunnel is removed to allow for the stabilization of the overhead vault. Only after the roof is secure do the crews descend level by level, gradually deepening the canal until they reach a depth of 12 meters below the level of the sea. The process resembles the slicing of a giant granite cake, executed with the force of explosives and the power of massive hydraulic excavators. But this is just the beginning. While explosions are effective for bulk removal, they leave behind jagged scars, irregular protrusions, and deep fissures in the stone walls. In a standard road tunnel, these imperfections are simply covered with layers of thick concrete. Why is a smooth surface absolutely critical for a maritime tunnel? In a roadway, air resistance is negligible, but in a channel filled with water, wall roughness creates violent turbulence. If the water flows in a chaotic or swirling pattern, a ship passing through loses its hydrodynamic control and steerability. The transition to the next level of precision is therefore mandatory to ensure vessel safety. The Norwegians utilize a technology typically reserved for high-precision industrial cutting to solve this problem. Diamond wires, consisting of heavy steel cables encrusted with industrial-grade diamonds, rotate at staggering speeds to slice through the granite. One can notice how the cable moves with fluid consistency, biting into the rock as if it were soft butter. This process leaves the interior walls perfectly smooth, ensuring that the water will eventually flow without any frictional resistance. It is the union of the raw strength of dynamite with the delicate precision of jewelry applied on a monumental engineering scale. Every meter of the wall is polished to prevent the formation of dangerous eddies or currents. Building the physical cavity represents only half of the technical battle. The true challenge begins at the moment the engineers finally invite the ocean to enter the finished chamber. 100 trillion liters of North Atlantic water could potentially surge into the cavernous space. The sheer kinetic force of such a massive torrent would annihilate the internal infrastructure and potentially trigger a total collapse of the structural walls. Why is the controlled introduction of water considered the most delicate hydraulic operation of the century? A sudden breach would result in catastrophic structural failure. To prevent this, the flooding process will be executed with extreme technical precision to balance pressures. During the entire construction phase, the tunnel remains perfectly dry, shielded by massive temporary steel dams positioned at both extremities. Inside this pressurized dry cocoon, engineers install systems that rely on advanced optoelectronics and automation. The equipment gradually fills the interior with specialized technology. One can notice that traditional industrial floodlights, which could easily blind captains, are absent from the design. The tunnel will instead be illuminated by continuous, unbroken LED strips that stretch along the entire length of the passage, resembling a futuristic landing strip. These light systems do not merely provide visibility. They function as the primary navigation array. It gets more complex further on. In a confined rock environment, GPS signals may fail or suffer from severe interference. Consequently, captains will guide their vessels by following color-coded light lines that provide a visual representation of the safe trajectory. When every internal system is verified, the flooding will finally commence. Special valves allow water to enter at a controlled rate, balancing the internal and external pressure ton by ton. Only when the internal level is identical to the outside sea level are the heavy steel dams removed. The process is only gaining momentum. Once the barriers are lifted, the sea finally occupies the space inside the mountain. But how do operators control ships weighing thousands of tons within a rigid stone tube? The tunnel will operate using a strictly regulated one-way traffic system. Ships will travel toward the north for a duration of 60 minutes, and then the flow of traffic will reverse to the south during the following hour. A dedicated vessel traffic center monitors every movement, functioning with the same precision as an airport control tower. Radars, thermal sensors, and high-definition infrared cameras keep watch over every single inch of the passage. It is visible how the automated systems track the speed and position of each hull. If a vessel stops, the system detects the anomaly within a fraction of a second. The tunnel entrance is a masterpiece of defensive engineering designed by the Snohetta architectural firm. The mountain banks are carved into stepped stone terraces. At first glance, this might look like a decorative choice, but in reality, these stone steps serve as critical energy buffers. They function by breaking the immense force of the waves before the water enters the narrow tunnel mouth. One can notice how the engineering utilizes geometry to tame the natural environment. However, innovating on this unprecedented scale requires significant financial resources. The price was originally calculated at approximately 426 million euros. But as is common with projects involving massive tunnels and mountains, the complexity continues to grow. These rising technical challenges ensure that the final stages of the project remain under constant observation. Thus, the structure is prepared for the next phase of its life cycle. 880 million euros is the current projected cost for the infrastructure, representing a staggering increase that doubled the initial budgetary estimates. Global inflation, unforeseen geological complexities, and the rising market price of construction materials caused the financial projections to explode. This fiscal expansion triggered an immediate political crisis within the administration. The Norwegian government eventually made the decision to freeze the entire project, raising a fundamental question about whether spending nearly 1 billion euros was justified simply to shave a few minutes off a maritime journey. Why did the national parliament decide to intervene and reverse the suspension? Direct political mediation led to a critical realization among lawmakers. This initiative is not merely about time intervals, but serves as a pillar for national strategy and the long-term survival of regional logistics. Consequently, negotiations with primary contractors were reopened to scrutinize every cent of expenditure without compromising structural safety. One can notice how the equipment remains idle as officials wait for the new formal approval expected in the year 2026. Giant dimensions define the tunnel, yet its physical capacity remains finite and subject to strict limitations. Supercontainer ships that drive the global economy, specifically those belonging to the Panamax class, possess a beam width far too large to enter the passage. These massive vessels will continue to navigate the external storms and heavy seas of the open coast. At first glance, this seems like a failure of design, but in reality, the tunnel was never intended for transoceanic giants. It was engineered specifically for the coastal fleet that maintains the essential supply lines of Norway. Scientists estimate that 81% of all current maritime traffic in the region will be able to utilize the tunnel safely. The true economic benefit will manifest through fuel efficiency and the newfound regularity of schedules. Currently, vessels burn through tons of diesel fuel while struggling against massive waves or remaining anchored for days waiting for weather windows. With the completion of the tunnel, the route is shortened, but the primary mechanical advantage is that the engines no longer fight against external resistance. But this is just the beginning. For smaller vessels, the reduction in fuel consumption can reach as high as 60%. It is a significant green victory obscured behind a massive project of reinforced concrete. Lower emissions and reduced maritime risks ensure that deliveries are guaranteed regardless of the weather outside. Fish reaches the market fresh and passengers arrive safely at their destinations. If the scale of this project seems like madness, it is because one does not understand the technical culture of Norway. This is a nation that treats solid granite as if it were soft butter. They do not merely construct tunnels. They are obsessed with the engineering of the underground. More than 1,100 road tunnels currently pierce the rugged Norwegian landscape. 50 of these structures dive deep beneath the floor of the ocean. For the average Norwegian citizen, entering the darkness of the earth is an action as banal as visiting a local supermarket. They hold engineering records that would cause international experts to break into a cold sweat. One can notice the immense scale by examining the Liardal Tunnel, which stands as the longest road tunnel in the world with a length of 24.5 kilometers. Driving through this specific passage requires 30 minutes of continuous underground travel. To prevent drivers from falling asleep or experiencing claustrophobia, engineers implemented advanced lighting psychology. At intervals of exactly every 6 kilometers, large caverns appear, illuminated with a brilliant blue light that mimics the dawn. This visual stimulus effectively tricks the human brain to maintain alertness and a sense of calm. The process of innovation is only gaining momentum. One can also observe the ongoing work on the Rogfast project. Engineers are currently constructing the deepest underwater tunnel on the planet, descending to 392 meters below the surface of the sea. The water pressure at such a depth is mathematically overwhelming for any standard structure. However, this is not the most impressive technical feat of the site. Down in that pressurized darkness, they are building something that seems physically impossible to the uninitiated. Underwater traffic roundabouts are being carved into the rock. Imagine driving a vehicle nearly half a kilometer below the waves through a subterranean intersection. Thus, the steel and stone are transformed into a functional network deep beneath the earth. 1,000 feet beneath the surface of the Norwegian landscape, travelers encounter a circular illuminated junction where a subterranean choice presents itself. Turn toward a hidden island or continue moving toward the mainland. It is an entire city of concrete built under the sea, showcasing a complexity that rivals surface architecture. Why did the Norwegian engineers pursue such an intricate underground network? For Norway, the Stad Ship Tunnel is not a solitary miracle or an accidental discovery. It represents the next logical progression in a long lineage of underground engineering triumphs that have defined the nation for decades. They have already mastered the technical art of keeping water out of massive automotive tunnels with absolute precision. The engineers are now simply inverting that established logic to keep water inside a tunnel designed for ships. It seems simple at first glance, but in reality, this reversal requires a complete rethinking of structural pressure and hydraulic balance. What comes next in this progression? Norwegian ambition does not terminate at the edge of solid rock formations. They are already analyzing fjords that are far too deep for traditional underground tunnels and significantly too wide for standard suspension bridges. The proposed solution involves the creation of submerged floating tunnels. Imagine two giant concrete tubes floating 30 meters below the surface of the water, held in place by pontoons on the surface and anchored firmly to the seabed. Huge ships would pass directly over the structure, cars would drive through the interior of the tubes, and massive waves would pass by without affecting the stability of the passage. If the ship tunnel appears unusual to the observer, the floating tunnel is pure science fiction becoming a tangible reality. The process is only gaining momentum as designs move from blueprints to the physical world. But returning to the present state, the impact of this specific project extends far beyond the limits of engineering. One can notice how the rock extracted from the mountain is not treated as waste or discarded material. Those 3 million cubic meters of stone will be repurposed to construct an entire new district in the neighboring city of Molloy. Houses, hotels, and commercial centers will be erected upon the very entrails of the mountain that previously blocked the path of travelers. It gets more complex further on as the project integrates with the local economy and tourism. There is also the human factor, as the tunnel will inevitably become a global magnet for visitors. A dedicated observation platform is being constructed so that people can witness the surreal moment when a giant cruise ship shuts down its storm radars and glides silently into the earth. The camera glides along the smooth stone walls as the vessel enters the mountain, marking the final victory of human ingenuity over the brute force of the natural elements. In the final analysis, The Stad Ship Tunnel is more than a safe passage for maritime traffic. It stands as a monument to technical stubbornness and the refusal to be stopped by geographical barriers. Thus, the steel and concrete structures reach their completion, opening the road to a new era of coastal navigation. $27 billion is the combined astronomical cost of two of the most massive defensive walls ever constructed in the modern era. On one side stands a steel scar that tears through scorching deserts for nearly 3,200 kilometers, designed to redirect and contain human flows. On the other side, a titanic concrete shield plunges into the freezing waters of Japan, erected for the sole purpose of stopping the ocean itself. Why is such a monumental investment required for these physical barriers? It might seem simple to just stack materials along a line, but the sheer scale of the environment renders conventional construction impossible. Only by overcoming extreme geological resistance and the relentless kinetic energy of the sea can these structures achieve their purpose. Engineers responded to the mortal barrier of waves and wind with mathematics, dynamite, and reinforced concrete. Soon, while a storm 30 meters high rages outside and destroys everything in its path, a ship will navigate calmly through the heart of a mountain. One can notice how the vessel moves under soft light-emitting diode lamps, completely oblivious to the chaos left behind. The mountain remained unmoved, but the technology was developed to pass directly through its core. This transition to the next level of engineering allows for a total bypass of natural obstacles. How is it possible to drive steel posts 9 meters in height into shifting sands and solid rock? The process is only gaining momentum. Specialized drilling rigs must first penetrate the surface with immense torque. Simultaneously, the question remains of how one can pour concrete for a barrier 15 meters high while the Pacific Ocean launches waves with devastating force. The equipment gradually stabilizes the forms against the water. It gets more complex further on as the anatomy of these megastructures is dissected, from the granite trenches of Arizona to the interlocking tetrapods of Fukushima. Strength is forged through the brute force of metal and stone. 3,200 kilometers is the distance the borderline stretches across, traversing terrain that changes radically with every single mile. Construction of these artificial frontiers begins long before any pillar touches the sky. In the United States, the initial challenge is not political, but purely geological in nature. At first glance, the desert seems like a uniform expanse of dust, but in reality, the subsurface composition dictates every mechanical choice. Heavy equipment faces constant the threat of being swallowed by soft sand. In regions such as Arizona and California, the ground transforms into a natural armor of granite and weathered rock. One can notice the slow movement of diamond-tipped drills struggling against the volcanic layers. The camera glides along the jagged trenches where explosives are carefully placed to crack the stone. Dust slowly settles after each controlled detonation, revealing the path for the steel bollards. It does not end at this stage, as the transition to more stable ground requires a completely different set of hydraulic parameters. Everything only gets more complicated as the elevation changes and the heat rises to extreme levels. The steel beams are lowered into the ground by cranes with millisecond precision. From here, the transformation moves to the next phase of processing as the wall extends further into the horizon. 1 meter and 80 centimeters to 3 meters is the impressive depth required for the foundation trench before any structural steel can be positioned. Why must engineers reach such extreme depths for a simple barrier? A fence might seem superficial, but these 9-meter-high steel posts must remain immovable against wind forces capable of uprooting mature trees, meaning the stability of the entire project depends strictly on the geological composition hidden beneath the surface. Topography teams begin by drilling soil samples and calculating exact elevations with millimetric precision. The first physical confrontation involves the excavation of the continuous foundation trench. One can notice how the excavation unfolds, not as a random pit, but as a precise technical channel measuring between 60 and 80 centimeters in width. Standing at the bottom of this trench, a person would be positioned beneath walls of earth nearly double the height of an average human. In soft soil conditions, standard hydraulic excavators manage the displacement easily, but much of the border consists of impenetrable rock formations where common machinery becomes entirely ineffective. Heavy artillery in the form of massive hydraulic breakers must be deployed to the site. These attachments, often the size of a compact car, function as giant pneumatic hammers mounted on large-scale excavators. One can observe the heavy steel bits striking the rock surface repeatedly to fracture the terrestrial crust and dislodge massive stone fragments. The sound of metal hitting stone is constant and deafening, while progress is often measured in mere inches per hour. It only looks obvious that such force is necessary, but in reality, this is the only way to penetrate the most stubborn geological layers. But this is just the beginning of the process. To accelerate this brutal phase and ensure the required structural accuracy, the trencher is brought into operation. This machine operates with heavy-duty diesel engines producing between 250 and 400 horsepower to drive a colossal chainsaw-like boom. It seems simple at first glance, but the chain is designed to slice through hardened earth and rock, as if the ground offered no resistance. The process is only gaining momentum as the machine moves forward with mechanical persistence. The equipment gradually cuts perfectly vertical walls while deepening the trench to the exact level specified by the engineering blueprints. Simultaneously, the rotating teeth of the chain grind any remaining rock into fine debris, leaving the floor of the trench flat and clear of obstructions. It is visible how an integrated conveyor system ejects the pulverized waste material to the side in a continuous stream. Everything only gets more complicated without such specialized automation. Thanks to this mechanical beast, a task that would normally require several weeks of manual braking is completed in just a few days. Hundreds of meters of trench are processed continuously, leaving a perfectly leveled opening in the earth ready for the next phase. The foundation remains open and stabilized, awaiting the arrival of the steel components. 10 millimeters is the precise thickness of the steel walls forming the hollow square or circular tubes that serve as the primary structural pillars of this massive barrier. Why is a hollow design chosen for components that must reach a height of nearly 9 meters? This configuration is a strategic engineering decision intended to reduce the total mass for logistics. But in reality, this weight reduction is only temporary, as it conceals a structural secret that will be revealed as the installation progresses. At first glance, the assembly appears to be a simple sequence of positioning posts, but the process is only gaining momentum. A framework of steel constructed from vertical bars and horizontal loops is lowered into the trench to function as a metallic spine along the boundary. One can notice how the equipment gradually prepares the site before a layer of reinforced concrete, ranging between 10 and 20 centimeters in thickness, is poured directly over this internal skeleton. This creates a flat, stable, and incredibly strong base, capable of supporting the colossal weight of the steel panels without sinking or tilting. As the concrete cures and fuses with the steel cage, it forms a continuous foundation block that resists massive torsional forces. This ensures the wall does not yield under the relentless pressure of desert winds. With the foundation set, the site transforms into an open-air industrial assembly line. Transition to the next level. The hollow bollards arrive stacked on heavy-duty cargo trucks, secured with steel straps to prevent the heavy tubes from shifting during transit. Each of these individual posts can weigh between 250 and 400 kilograms. The camera glides along the storage area, where mobile cranes lift bundles of these components with the hiss of hydraulics. In a temporary fabrication zone, welders utilize high-power machines to fuse the posts into modular panels. Generally, each panel consists of 4 to 6 posts, depending on the required width of the section. It seems simple to align them one by one in the trench, but in reality, welding these giants on the ground drastically accelerates the installation speed. The process is only gaining momentum. Lifting a steel panel 9 meters high and 9 meters wide in the middle of the desert is an operation of high risk. The crane elevates the structure, which now begins. 1 meter and 50 centimeters is the exact distance the concrete base extends outward into the earth to form a reinforced subterranean platform. Why is this expansion of the foundation necessary when the steel pillars are already driven deep into the soil? At first glance, the vertical support seems sufficient, but the underground wings distribute the massive vertical weight and function as an impenetrable shield against any attempt to breach the perimeter from below. The hollow steel tubes do not remain empty as liquid concrete is poured into their cores. One can notice how the mixture settles and hardens, transforming each individual post into a high-strength composite pillar of metal and artificial stone. This internal reinforcement increases the overall structural resistance exponentially. The process is only gaining momentum. It is visible how the outer surface undergoes cleaning with high-pressure water jets to strip away every trace of welding residue and industrial oil. This ensures that the subsequent protective paint and anti-rust layers adhere with absolute precision to the metal. And this is not the limit of the defensive architecture. Military personnel install razor-sharp concertina wire along the upper sections of the towering structure to eliminate the possibility of scaling the barrier. While these measures address the management of land borders, Japan must confront a physical force of nature that cannot be deterred by wire alone. $12 billion is the sum the nation invested in one of the most ambitious coastal defense projects in history, following the catastrophic events of 2011. The objective involves the construction of nearly 400 kilometers of massive seawalls along the Tohoku coastline. These structures are not mere fences, but colossal concrete barriers rising 15 meters into the air. This height is equivalent to a 5-story building, and every meter is designed to buy precious minutes for civilian evacuation during a surge. It only looks obvious to build a wall, but the challenge lies in the unstable composition of the impact zone. Most of the coastline consists of weak, sandy soil that loses all structural integrity when it becomes saturated with water. The equipment gradually prepares the site, because building such a heavy mass on this geological soup would result in the wall sinking or sliding directly into the ocean. Before the first drop of concrete is poured, teams must perform the grueling task of clearing debris left behind by previous disasters. This preparation ensures the ground can support the weight of the massive slabs. Everything only gets more complicated as the engineers move from clearing to stabilization. The material is ready to move to the next processing phase without haste. 24 meters is the staggering depth that hydraulic excavators must reach to carve out foundation pits for the coastal defenses. Why is such extreme excavation necessary when the visible wall appears much shorter? At first glance, the structure above the surface seems to be the primary defense, but in reality, the stability of the entire barrier depends on a base that is deeper than the wall is tall. This design functions like a concrete iceberg, where the vast majority of the mass and structural integrity remains submerged and hidden from view. Everything only gets more complicated as the proximity to the ocean increases. Construction requires the constant operation of mixing stations and heavy machinery, while workers contend with the relentless movement of tides and seasonal rains. One can notice how engineers drive temporary containment walls or cofferdams into the seabed to block the seawater, effectively creating artificial dry islands for the equipment to operate. This process is only gaining momentum. The unstable sandy soil undergoes a rigorous stabilization process through the high-pressure injection of layers of crushed stone and compacted sand. It is visible how steel or deep concrete piles are driven further into the earth to reinforce these subterranean layers. Over this meticulously prepared substrate, a massive and wide foundation slab is poured. But this is just the beginning. It only looks obvious that a wall should stand upright, but this slab acts as a giant foot, distributing the weight across a broad area to prevent the structure from being pushed inland by the sheer force of the Pacific. Once the base is secured, the process moves to the assembly of rebar cages. Dense and complex skeletons of steel bars are tied together with millisecond precision to provide the necessary tensile strength. Giant molds are positioned around these steel skeletons as the concrete is pumped inside, section by section, through heavy-duty hoses. One can notice the slow movement of the booms as they fill each segment. Each individual block, stretching dozens of meters in length, undergoes a controlled curing process before being connected to the next. Transition to the next level. This creates a continuous, winding barrier that follows the natural curves of the coastline. A simple vertical wall would suffer the full concentrated impact of a wave all at once, which poses a risk of structural failure. Because of this physical reality, Japanese engineers design inclined surfaces and integrated steps that force the water to break and dissipate its kinetic energy. The defense does not end at the wall itself. Thousands of specialized concrete units, such as tetrapods and dolossi, are stacked in chaotic but calculated piles at the seaward base. One can notice how these geometric shapes interlock to form a porous armor. The equipment gradually moves further along the shore, repeating the cycle of reinforcement and casting. The material remains in place, ready to withstand the pressure of the ocean for decades. 400 meters before the tide even reaches the main barrier, concrete breakwaters function as a primary line of defense. Why is it necessary to position these heavy blocks so far out in the turbulent water? It only looks obvious to build a single wall, but in reality, these detached structures force the waves to break early and lose their destructive kinetic energy. The water flows around them in chaotic patterns, dissipating its force before it can strike the primary seawall. One can notice how the external surface of the main structure is reinforced with a specialized armor layer. This protective skin consists of massive precast concrete panels that are interlinked to form a seamless shield. Heavy-duty cranes lift these individual components and fit them together with the precision of a giant puzzle. This secondary layer ensures that the core of the wall remains untouched by the constant erosion of salt water and the impact of heavy debris carried by storm surges. On the landward side, the engineering focus shifts to internal stability through complex drainage systems. These channels ensure that heavy rainwater does not accumulate behind the wall and create hydrostatic pressure that could destabilize the entire foundation. The process is only gaining momentum. $27 billion in total project costs, millions of tons of reinforced concrete and structural steel, and hundreds of kilometers of physical barriers define this endeavor. A fascinating contrast in materials and strategic purposes becomes visible when observing these two megastructures side by side. The American steel structures reach toward the sky with a focus on height and transparency to manage human movement across the desert landscape. In contrast, the Japanese concrete barriers utilize sheer mass and subterranean depth to withstand the raw physical power of the Pacific Ocean. Both projects stand as physical monuments to human determination and technical capability. It seems simple to view these as mere walls, but in reality, they prove that with sufficient resources and advanced engineering, it is possible to draw a definitive line in the sand or the sea. Whether the objective is protection against criminal cartels or the mitigation of tsunamis, these barriers represent a perpetual search for security amidst global chaos. The equipment gradually completes its task, but the struggle between static engineering and the dynamic forces of the natural world never truly concludes. It does not end at this stage. The conflict merely shifts in scale and intensity. 99 million tons of earth and rock are moved in an effort that mirrors the relocation of an entire mountain. One can notice the absence of heavy machinery in this specific historical context, as the work was performed using only human hands. This titanic expenditure of energy was not intended to create a tomb for ancient royalty like the pyramids of Giza. Instead, the labor was directed toward a goal that seemed even more impossible, which was to resurrect a dead landscape. In a region where the vast forests had completely disappeared and the local water sources had evaporated, the farmers of Giza began a total transformation of the environment. The process is only gaining momentum as the narrative moves toward the restoration of the soil. Thus, the engineering of the past and present converge to protect and reclaim the territory. 106,000 acres of forest returned to life in a country once ravaged by starvation, representing the greatest feat of ecological engineering of the century. Why did this restoration succeed without the manual planting of a single tree? The answer challenges the established foundations of environmental science and conventional nature conservation. To comprehend the scale of this transformation, it is necessary to examine the period when environmental collapse began. Ethiopia, situated in the East African highlands, was not always the arid wasteland depicted in the news reports of the 1980s. At first glance, the dust seems permanent, but in reality, this region was once celebrated as the Garden of Africa. Dense and vibrant forests previously covered more than 60% of the entire national territory. Deep rivers continuously fed one of the most fertile regions on the African continent, maintaining a complex hydrological balance. But this paradise entered a spiral of destruction that resembles a cinematic collapse. Within just a few decades, Ethiopia lost more than half of its total forest cover. By 1982, the situation reached an apocalyptic state. Forest coverage had plummeted to a mere 3% of the land area. Of the original 77,000 square miles of green canopy, only 12,000 square miles remained. One can notice how the landscape shifted as life was replaced by a hard, dry crust of earth. But this is just the beginning. The forests did not vanish through a supernatural occurrence. They were forced into the abyss by relentless human pressure and the immediate needs of survival. Centuries-old trees were systematically felled for firewood to provide basic heat and energy. Entire forest ecosystems were incinerated to create desperate agricultural fields for a growing population. Everything only gets more complicated as the biological cycle breaks. When the trees disappeared, the earth lost its protective skin and its structural integrity. Without a complex network of roots to anchor the soil, the ground lost its capacity to retain moisture and absorb rainfall. The process of desertification gained momentum. The rain stopped falling as the local microclimate shifted. Rivers dried up into dusty channels, and the wind began to blow away the remaining fertile topsoil. What remained was a scorched red desert incapable of sustaining life. It only looks obvious that the land was dead, but the underlying mechanisms were completely shattered. The inevitable consequence arrived in 1983. The Great Famine became the most devastating tragedy in the history of the nation, claiming the lives of more than 1 million people in just 2 years. The camera glides across a landscape of total depletion as the world watched the disaster unfold in real time. The material conditions for survival had vanished, leaving only the remnants of a once thriving ecosystem to face the wind. The transformation of the landscape concludes this phase, opening the road to a radical new approach to restoration. 100% of the landscape resembled a scorched wasteland, where the fundamental question was how to stop the hemorrhaging of an entire ecosystem. The earth remained clinically dead, under a sun that offered no reprieve for the exhausted soil. Why did every traditional attempt to revive the greenery end in such total devastation? It seemed logical that planting new life would succeed, but the reality of the environment proved far more hostile than any laboratory simulation. International projects funneled millions of dollars into massive reforestation efforts that ultimately failed with catastrophic consistency. Engineers and laborers planted millions of saplings across the cracked terrain, but 90% of these young trees perished within a few short weeks. One can notice how the 40°C heat cooks the plants alive, turning hopeful green shoots into brittle brown husks in a matter of days. If the heat did not destroy them, hungry livestock consumed every remaining leaf, leaving nothing behind but dust. Planting new trees was objectively expensive, agonizingly slow, and proved to be entirely futile in the face of such extreme conditions. But this is just the beginning of a shift in perspective. Everything only gets more complicated when resources are depleted and hope vanishes. Tony Rinaldo, an agronomist working within the heart of this environmental crisis, observed a detail that others had overlooked for decades. At first glance, the landscape was covered in useless weeds and parched shrubs that appeared to be nothing more than desert debris. In reality, these scattered growths were not waste, but the visible crowns of a massive underground forest. The camera glides along the hardened surface of the earth, where deep root systems remain hidden from the naked eye. Thousands of years of biological history lay dormant beneath the crust, waiting for the right intervention. The process is only gaining momentum as the realization takes hold that the trees are already there, buried under the sand. It is visible how the soil protects these ancient structures, keeping the core of the ecosystem alive even when the surface appears barren. Instead of bringing in external elements, the focus shifted to the existing subterranean network. This revelation marked the transition to a completely different method of restoration. The underground forest represents a biological foundation that survived where surface seedlings could not. Thus, the transformation of the dead landscape began not with new life, but with the awakening of the old. 100 feet. That is the staggering depth to which the resilient root systems of the original vegetation extended into the arid earth. Although the surface appeared barren, the plants remained alive in a state of deep biological dormancy, waiting for a single catalyst to trigger their reawakening. Why did the landscape remain a desert if the roots were still functional? The answer lay in the constant pressure of grazing and the lack of systematic care. But without a controlled intervention, the potential for regrowth remained locked beneath the sun-bleached soil. Farmer-managed natural regeneration, or FMNR, proved to be the unexpectedly simple solution to this environmental stagnation. This method bypassed the need for expensive nurseries or the transport of fragile saplings from distant regions. One can notice how a simple pruning knife becomes the primary tool for restoration in this technical framework. Farmers carefully selected existing stumps and systematically removed the weaker branches. It is visible how they protected only the 3 or 4 most robust trunks, allowing the plant to focus its energy. The trees utilized their massive pre-existing root structures to surge toward the sky at a rapid pace. This process required no additional irrigation systems and functioned entirely without the application of costly chemical fertilizers. But this is just the beginning. It seems simple to prune a tree, but in reality, no biological growth can be sustained without a consistent supply of moisture. The water had abandoned the region decades ago, leaving the terrain dehydrated and impenetrable. To reverse this, the residents of Humbo transformed into geographical engineers by necessity. They operated without the assistance of diesel-powered tractors or large-scale government funding. What remained were old shovels, heavy pickaxes, and a collective determination to reshape the landscape. They studied the bare hills and reconstructed a topographical map of ancient water flows from memory. One can notice the start of one of the largest manual labor operations in agricultural history as the community mobilized. Men and women moved heavy stones under the intense heat to construct thousands of micro-dams and terraces. The volume of material moved reached 99 million tons of soil. 99 million tons is a figure equivalent to the weight of hundreds of massive skyscrapers. Every pound was moved bucket by bucket and stone by stone across the rugged terrain. The technical objective was to fundamentally alter the physics of the ground surface. They excavated infiltration ponds and carved contour trenches designed to trap every millimeter of precipitation. The process is only gaining momentum. When the rain eventually fell, it no longer formed destructive mudslides that stripped the topsoil away. Instead, the water encountered physical barriers that forced it to decelerate and settle. The camera glides along the stone dikes where the liquid is compelled to infiltrate the thirsty earth. Ravines that once acted as open wounds in the landscape were systematically blocked with heavy masonry. The logic of the engineering was absolute, ensuring that not a single drop of rainwater could escape the perimeter. One can notice the red, dusty earth gradually transforming into a giant geological sponge. This subterranean reservoir began to nourish the dormant roots waiting in the darkness below. But the physical engineering of the soil was only half of the required transformation. Social engineering presented an even more complex challenge for the community to navigate. For the forest to successfully return, a difficult decision was made to prohibit livestock from grazing freely on the hillsides. For many generations, goats and sheep had consumed every emerging sprout before it could mature. Transition to the next level. The material remains in place, and the ecosystem begins its slow transition towards stability. Thousands of heavy hooves once compacted the local soil until the earth reached the density of solid cement. Why did the villagers decide to wall off their own hills and banish the livestock? This decision meant voluntarily cutting off their primary source of sustenance and liquid capital, representing a sacrifice of immense proportions. But without this intervention, the land would have remained a sterile wasteland, unable to absorb a single drop of moisture. The community divided the landscape into 3 strictly regulated zones. The valleys were dedicated to irrigation systems, while the middle slopes were reserved for structured agriculture. The highest peaks were declared sacred and untouchable, set aside exclusively for forest regeneration. One can notice how a sudden silence descended over the heights as the constant rhythmic drumming of hooves and the sound of hungry mouths tearing at the grass vanished completely. Biological mechanisms began to operate once the pressure was removed. The reaction from the natural environment was explosive. In the span of just one rainy season, vegetation returned with a green fury, and where previously there was only bare stone, dense shrubs began to blanket the terrain. But this is just the beginning. In 5 years, the plant cover in the protected areas increased by 200%. The iron discipline maintained by the villagers bought the necessary time for the ecosystem to heal. One can notice the morning humidity beginning to last twice as long, creating a cool microclimate that functioned as a magnet for insects. These small organisms, in turn, attracted bird species that had not been observed in the region for decades. The entire chain of life was being reconstructed, link by link, through the slow accumulation of organic matter. It gets more complex further on. The impossible occurred as water returned to the landscape. The liquid did not arrive via tanker trucks or plastic pipes, but began sprouting directly from the earth itself. It is visible how the soil regained its function as a natural sponge. One must recall the 13 natural springs of the region that had dried up completely, remaining only in the fading memories of the village elders. Thanks to the newly planted trees and the strategically placed stone terraces, rainwater infiltrated deeply into the geological layers, successfully recharging the underground aquifers. 6 of those 13 dead springs began to gush crystal clear water once again. At first glance, this might have seemed like a temporary miracle, but in reality, it was the result of precise hydraulic restoration. These springs now maintain a steady flow throughout the entire year, regardless of the season. The transformation of the hydrologic cycle concludes this phase, opening the road to long-term stability for the entire valley. 106,000 acres was the initial extent of this transformation within the borders of Ethiopia. Why did the dry riverbeds suddenly transform into gentle currents that deposit fertile silt along the banks? This transition occurred because the soil regained its ability to retain moisture through the systematic restoration of natural cycles. The water learned to stay in the earth rather than evaporating or flowing away across the parched surface. This hydraulic success proved that the land was never truly dead, but was merely suffering from extreme dehydration. By healing the topsoil, the local community successfully repaired the entire water cycle. One can notice how domestic life changed instantly for the local population. Women who previously spent interminable hours walking under the sun to fill jars with muddy liquid now utilize clean water sources situated near their homes. But this is just the beginning. The return of water triggered a profound economic revolution that moved through the villages like a physical force. With the soil remaining moist and nutrient-rich, agricultural production surged by 85%. This shift meant the average household income increased by 76% across the region. At first glance, it seems simple, but in reality, this growth ended the dependence on foreign food aid and allowed farmers to sell their own surplus products. The process is only gaining momentum. Where hunger once dominated the landscape, one can now see beehives producing honey and sustainable timber being harvested for construction. The equipment is simple, yet the results include the sale of carbon credits to the United Nations. The forest effectively became a biological bank, generating compound interest in the form of diverse life. It is visible how the model soon exploded beyond national frontiers. What started on a local scale spread like a positive fire across the African continent. 12 million acres of desert were converted into productive land in Niger using these same fundamental methods. The tools used are nothing more than a simple knife and stone to manage the regrowth of hidden root systems. In Burkina Faso, barren hills were replaced by dense forests that now provide food for millions of people. This serves as definitive proof that saving the planet does not require high-end technology, but rather scalability and a deep respect for natural systems. It gets more complex further on as the scale of human effort is revealed. We return to the question that initiated this journey regarding the possibility of creating a forest without planting a single tree. The answer is physically engraved upon the landscape of Ethiopia. 99 million tons of earth were moved by hand during this massive restoration project. This labor did not construct a cold stone monument, but instead built the foundation for the future of life on the planet. Everything only gets more complicated when one considers the potential lying dormant beneath the surface. Beneath our feet, the solutions often wait for the right conditions to emerge. Thus, the steel-like resolve of the community concludes this phase of the environmental restoration. 122 degrees Fahrenheit is the temperature frequently reached under the relentless sun of the Saudi Arabian peninsula. Why is human life on a massive scale even possible in a region where 98% of the surface consists of scorching sand? The high plateau topography effectively blocks rain clouds, creating a physical barrier that prevents moisture from the sea from reaching the interior. However, 5 billion gallons of fresh water now flow every single day beneath this unforgiving landscape. Ancient roots and dormant seeds remain hidden beneath the surface, waiting for the moment human industry stops resisting the environment and begins working in alignment with it. It only looks obvious that a desert must remain a wasteland of red dust, but in reality, the nature of the terrain only requires space to remember its original state. The modern era has introduced a thirst that exceeds the natural capacity of the land. Each citizen has access to only 68 to 90 cubic meters of natural water per year. This is not the limit of the crisis. One can notice how the absence of a single natural river or lake forces a total reliance on engineering. Engineers constructed a massive ribbon of steel and water, long enough to circle the entire planet Earth 35 times. The camera glides along the vast network of pipes buried beneath the dunes. It seems simple to suggest the desert is empty, but the transformation into a green-gold oasis proves the strength of industrial alignment with the forces of the Earth. 5 billion gallons of water move through this artificial arterial system with mechanical precision. This represents the largest life support network ever conceived in human history. The process is only gaining momentum as the infrastructure expands across the desert floor. Dust slowly settles over the construction sites of new pipelines that defy the climatic maps. The equipment gradually installs heavy-duty pumping stations to maintain the pressure of the subterranean flow. Survival was once a game of luck lasting for millennia in these arid zones. Now, the hydraulic systems ensure that the water flows regardless of the heat. Nature does not require reinvention, but rather the strategic application of industrial power to unlock its potential. This provides the necessary foundation for a nation without surface water to challenge the geographical certainty of death. The water reaches its destination through the steel veins, concluding this phase of the regional transformation. 500 cubic meters of water is the absolute poverty threshold established by the United Nations for a single human being. Why is such a low figure considered a critical limit for survival? The answer lies in the physiological reality that while a person can survive 3 weeks without caloric intake, the body fails within a few days when deprived of hydration. This volume stands in stark contrast to the 9,000 cubic meters enjoyed by the average American citizen. In this environment, every liter becomes a literal determinant of existence. It seems simple to look toward the horizon for resources, but in reality, the solution lay beneath the scorched surface. To delay an inevitable end, they began to penetrate deep into the sand in pursuit of concealed liquid treasures. These are ancient fossil aquifers, geological structures that required thousands of years of slow accumulation to form. But this is just the beginning. Starting in the 1980s, thousands of mechanical drills pierced the desert crust, extracting trillions of gallons from the depths. It only looks obvious that such an abundance would solve the problem, but in reality, this became a dangerous dependency. By the year 1992, annual consumption escalated to 7,500 billion gallons. To visualize this scale, imagine a volume of water sufficient to fill more than 27,000 Empire State Buildings to their absolute summits. One can notice how the water was utilized as if the supply were infinite. The process is only gaining momentum, yet a harsh geological fact remains. Fossil groundwater does not replenish itself. It functions exactly like an oil well. Once the reservoir is depleted, it remains empty for eternity. The countdown for the region began to accelerate far beyond initial projections. In a span of only 25 years, the water table within the vital Al-Assa aquifer plummeted by nearly 500 feet. This was a silent but catastrophic collapse of the subterranean pressure levels. By the year 2012, 80% of the total groundwater reserves, which once amounted to 132 trillion gallons, had vanished. The nation was effectively consuming its own future. Desert agriculture, which initially appeared as a triumph of engineering, was devouring 6,500 billion gallons by the year 2015. Everything only gets more complicated as the limits are reached. Authorities were forced to apply the brakes with maximum industrial force. Thirsty wheat fields were either completely abandoned or underwent a transition to the next level through modernization. The equipment gradually changed as farmers installed precision drip irrigation systems and moisture sensors. Agricultural consumption subsequently dropped by 40%. Within the urban centers, municipal governments imposed heavy financial penalties on anyone caught wasting a single drop. It is visible how the society began to shift its relationship with the resource. But this conservation effort was merely a temporary bandage on an open wound. The population continued its upward trajectory, and the collective thirst showed no signs of abating. They required a new source that could be considered inexhaustible. The only infinite element surrounding them was the ocean. Why is raw seawater not a viable solution for a thirsty population? Drinking untreated salt water is a death sentence for the human metabolic system. Transition to the next level of engineering was the only option. To overcome the salt, they required industrial brute force on a scale never before witnessed in history. They decided to boil the sea. This is not a linguistic metaphor, but a physical description of a massive thermal process. The technology involves transforming salt water into high-pressure vapor to isolate the mineral salts. The equipment then facilitates the cooling of this vapor, allowing it to condense back into a liquid state of pure, potable water. The steam rises through the massive heat exchangers as the salt remains behind. The material is ready to move to the next processing phase without haste. 35 million people must be supplied with water every single day in one of the most arid regions on the planet. Why is such a massive industrial effort concentrated along the coastlines of the Red Sea and the Persian Gulf? At first glance, the process of removing salt from water seems straightforward, but scaling it for an entire nation results in a titanic steel infrastructure that operates on a level unseen anywhere else. 41 gigantic desalination plants currently function as the backbone of the Saudi Arabian water supply, acting as massive metal cathedrals of engineering. These facilities produce 3 billion gallons of fresh water every 24 hours. One can notice how the equipment gradually processes the tides, contributing 22% of all the desalinated water generated on planet Earth. This output is staggering when compared to other global powers. If one were to combine the capacity of every single desalination plant located in the United States, the total sum would represent less than 1/5 of what is produced by Saudi Arabia. This remains true even though the American coastline is significantly longer than that of the Arabian Peninsula. But this is just the beginning of the scale. The Ras Al Khair complex serves as the epicenter of this industrial storm. It is visible how this site functions not merely as a factory, but as an entire industrial city dedicated exclusively to the transformation of seawater. A single day of operation at this facility generates 264 million gallons of potable water. To put this volume into perspective, the daily output is sufficient to meet the needs of nearly 2 million American households. It gets more complex further on as the energy requirements are calculated. 2,400 megawatts of electricity are generated by the complex to sustain its operations. This power output is equivalent to the combined strength of 2 medium-sized nuclear reactors working at full capacity. Within the facility, hundreds of steel tanks, each as long as a professional football field, house the core process. The seawater inside is heated and subjected to a vacuum, causing it to evaporate instantly in a flash. The equipment moves and vibrates as the water undergoes this rapid transition. It only looks obvious to boil water, but in reality, this is a violent, high-pressure and high-temperature environment. The machinery is engineered with extreme durability in mind, designed to withstand these harsh conditions for 25 years without interruption. One can notice the thick insulation and heavy-duty alloys required to prevent corrosion from the salt. However, boiling the ocean requires a massive expenditure of resources. The process consumes a quantity of energy that was historically immense, previously requiring enough fuel to support 9 billion people in different contexts. The transformation of the raw brine moves toward the final stage of purification, as the heat levels are strictly monitored by automated sensors. Precision at a microscopic level replaced the reliance on raw heat in the next evolution of this liquid conflict. Why did the engineering shift from thermal energy to biological mimicry? A process as simple as boiling requires immense fuel, but the physics of nature suggested a more efficient path through the implementation of reverse osmosis. This transition moved the industry away from fire and steam toward the application of immense hydraulic force. Mechanical pumps exert extreme pressure to drive raw seawater against specialized polymer membranes. One can notice how these synthetic sheets serve as the final frontier of the entire filtration sequence. These membranes possess a thickness of only a few millionths of an inch. Such a scale is difficult to comprehend, yet the pores within these polymer sheets are so incredibly small that they function as an absolute physical barrier to contaminants. Sodium does not pass, minerals are rejected, and even microscopic viruses are blocked by the structural density of the material. What emerges from the opposite side of the barrier is pure water, filtered to a level of 99%. It gets more complex further on. At first glance, the energy required to create such pressure seems unsustainable. However, the system relies on modern energy recovery devices that capture and reuse hydraulic force. Because of this integration, new industrial plants consume only 2 8/10 kilowatt-hours to produce 264 gallons of fresh water. This is roughly the same amount of electricity required to power 10 light-emitting diode bulbs for a single hour. The equipment operates in a silent revolution across the landscape. 2/3 of the water currently flowing through urban centers is processed by these high-technology membranes. Every single glass of water consumed in the city of Riyadh has traveled through these microscopic filters, which are powered by a combination of conventional electricity and vast arrays of solar panels that gleam under the desert sun. But this is just the beginning of the engineering feat. The process is only gaining momentum as the challenge shifts from chemistry to geography. A significant majority of the population resides far from the coastline, situated in the arid heart of the nation. One can notice the immense scale of the problem when considering how to move the volume of an ocean across a desert. This creates the largest logistical challenge in the history of hydraulics. Water is an incredibly heavy substance to transport, and the terrain of Saudi Arabia is not a flat expanse. Engineers must move this mass to cities and villages located hundreds of miles away from the source. The transition to the next level of infrastructure requires overcoming both distance and elevation.